Welcome to our exploration of Splunking Cisco Isovalent data. Today, we'll cover the lab setup, attack simulations, and detections using tools like Tetragon and eBPF. As we proceed, we'll see how these technologies integrate with Kubernetes and Splunk to enhance security and observability. Let's dive in. On this slide, we start by defining eBPF, Tetragon, and Cisco Isovalent. eBPF consists of safe, sandbox programs running inside the Linux kernel at hook points. Tetragon, powered by eBPF, is a runtime security and observability tool that emits process and network events integrated with Kubernetes identity. Cisco Isovalent provides cloud-native networking and security expertise, now integrated into Cisco. Understanding these components sets the foundation for our discussion. Here, the concepts are explained in a simplified manner. Think of the Linux kernel as the engine room of your computer, while eBPF acts as sticky notes monitoring the engine. Tetragon functions as a security camera reading those notes and labeling them by pod. Splunk is the detective board assembling clues and raising alerts. The process connects kernel events to detections, showcasing the flow of data from kernel events to actionable insights. Next, we'll discuss setting up the lab environment. We begin with a Kubernetes cluster using Kubernetes Goat. Tetragon is deployed as a daemon set on each node. Event sources such as process_exec, process_connect, and kprobes are enabled. Events are exported in JSON format and forwarded to Splunk's HTTP event collector. Validation in Splunk involves searching for a known pod and confirming process and network fields. This setup highlights the integration of Kubernetes and Splunk to monitor and analyze data. This slide outlines the types of data you'll see in Splunk. Process_exec tracks the start of processes, process_connect monitors socket connect telemetry, and kprobes handle custom kernel function hooks. Understanding why each type matters, whether it's spotting offensive tools, detecting scanning and exfil patterns, or identifying runtime anomalies, helps in pinpointing security issues. Correlating data allows us to identify the source and frequency of events. We now simulate an attack scenario involving a port scan from a pod, a form of network reconnaissance. Using specific Kubernetes commands, we initiate the scan from inside the cluster. Tetragon captures process execution and connect bursts, along with pod identity details. We focus on detecting offensive tooling, contextualizing where it runs, and correlating burst connections to enhance detection confidence. These insights help us understand potential threats within the network architecture. Following up on the attack simulation, this slide demonstrates how Splunk is used to detect pods running offensive tools. By searching the Cisco Isovalent process execution logs, we identify pods executing offensive commands like nmap. This search provides detailed insights into process names, parent processes, and executing nodes, representing a clear example of how Splunk tracks suspicious activities across the cluster. Why do we detect port scanning? It's often a precursor to lateral movement through mapping reachable nodes. Especially in Kubernetes, scanning behavior stands out due to narrow egress patterns in application pods. Runtime telemetry paired with suspicious tooling forms a strong signal for detection. Our recipe involves detecting execution, counting unique connections, and alerting on abnormal patterns from typical workloads. This approach strengthens our security monitoring. In this attack simulation, we explore curl to a suspicious domain, simulating outbound HTTP calls with insecure TLS flags. Observing curl execution and outbound connections helps identify potential beaconing behavior. Key detection points include ignoring TLS validation, which is a red flag, often used for payload fetching. Combining domain reputation and connect telemetry assists in rapidly identifying malicious activity. This scenario underscores the importance of comprehensive network monitoring. Finally, by analyzing curl executions in Splunk, we track insecure flags indicating potential threats. The search results show detailed metrics such as cluster name, pod details, and execution paths, helping identify abnormal traffic patterns. This process aids in preemptively detecting threats and understanding how malicious activities exploit network vulnerabilities. Our goal is to maintain a secure and resilient network infrastructure against evolving threats. In this slide, we're focusing on the combination of Atomic Red Team and Splunk's Enterprise Security Content Updates, or SQ. Atomic Red Team provides a suite of repeatable tests, including activities like curling insecure connections from a pod or creating a Linux user via kubectl. These tests help simulate real-world scenarios like supply chain attacks through NPM package installations. They're designed to be shared and rerun, ensuring consistent testing across environments.n/n. On the other side, SQ offers out-of-the-box Splunk resources, providing pre-built detections and analytic stories. This includes a detection catalog accessible via their research site, allowing you to map these resources directly to your telemetry, adjust thresholds, and apply Kubernetes context seamlessly. /n/n. The key takeaway here is treating detections like code. You should test, tune, version, and continuously validate these detections against real telemetry. This practice ensures your security posture remains robust and adaptive to evolving threats. Please visit research.splunk.com for more detailed information. In conclusion, our journey from visibility to resilience focuses on understanding not only the attacks but the underlying behaviors and misconfigurations that facilitate them. Leveraging Cisco Isovalent's eBPF-powered telemetry combined with Splunk's analytics, we're able to correlate system calls, process lineage, and network activities back to Kubernetes pod identities in real time, enhancing our observability. /n/n. To transform detections into actionable security measures, we must tighten role-based access control, enforce admission controls and runtime policies, and continuously validate our security posture with repeatable tests. /n/n. Remember the importance of small signals. For instance, an uptick in cprobe activity could signal potential kernel tampering, while an unexpected curl command might indicate a malware downloader. Likewise, unexpected package installations could be persistence mechanisms by attackers. /n/n. This approach, from visibility to detection, then hardening, and finally resilience, shapes a proactive defense strategy, equipping us to maintain a robust security environment against emerging threats.